Quantum computing is becoming a hot topic, but really, what is it? And why should we care? Imagine a world where problems that would take classical computers millennia to solve can be tackled in mere seconds. That's the promise of quantum computing. And it's not just sci-fi anymore. From breaking encryption to revolutionizing artificial intelligence, this technology could redefine our future. Hi, my name is David Estrine, and today we're diving into the fascinating world of quantum computing. We'll unravel the mystery of qubits and superpositions, exploring its game-changing applications in cryptography and machine learning. Unlike classical computer systems, which rely on bits that exist in a single state, either 0 or 1, quantum systems operate in a fascinating world where particles can exist in multiple states at the same time. The phenomenon is called a superposition. In classical computing, information is processed using bits, the familiar ones or zeros that you see hackers commonly have in the movies. These bits are based on defined states, as 0 represents off and 1 represents on. Quantum computing, however, introduces the concept of a qubit, short form for quantum bit, which can exist as both 0 and 1 at the same time. To help visualize this, think of a coin spinning in the air. While it's spinning, it's not just heads or tails. It's in a state where it can be considered a mix of both. Only when the coin lands and we observe it does it choose a definite heads or tails outcome. This spinning state, where it's both heads and tails simultaneously, is what we call the superposition in quantum mechanics. But there's a really fascinating part. This isn't just about 3 states, heads, tails, and a mix. In reality, there's an infinite number of possible states the coin can exist while spinning. In fact, for a single qubit, the number of possible superpositions is closer to infinity minus 2. This is because a qubit isn't restricted to just 2 extremes or a midpoint. It can exist in a combination of states described by probabilities that span an entire sphere. This incredible flexibility is what gives quantum computing its power, allowing it to process information in ways classical systems cannot. To truly understand the quantum superposition, we need to dive into the atomic level. Unlike planets orbiting the sun in fixed paths, electrons around an atom exist in a cloud of probabilities. This means an electron doesn't have a single well-defined position. Instead, it can exist in multiple positions at the same time, until we observe it. The act of measurement forces the electron to choose a specific position, collapsing its superposition into one definitive state. This strange, almost magical sounding behavior is one of the core principles that quantum computing is based on. By harnessing this concept, qubits can represent and process vastly more information than classic bits ever could. Up until now, we've been thinking about states like heads or tails on a single linear spectrum. But quantum mechanics challenges us to think differently. Instead of a line, let's use a graph. In quantum mechanics, the state of a qubit isn't just a single axis. Instead, it's a combination, or superposition, of these basis vectors. The qubit's position on the graph is determined by how much it aligns with each basis vector. In simple terms, it's part heads and part tails, described as a weighted combination of the two. We take this idea of basis vectors like heads or tails to the next level. These basis vectors don't just exist in isolation. They form a part of a vector space. A vector space allows us to represent any superposition of these states as a unique vector within it. Here's the key idea. The length of this vector is equal to 1. This is because the probabilities of the possible outcomes like heads or tails must add up to 100%. No matter how the vector shifts or rotates, the rule holds true. But again, this isn't just a few states. The number of possible states a qubit can represent is closer to infinity minus 2. Even though it can exist in an infinite range of superstates, at any given moment, the qubit is always in that one singular state. Let's think about a car driving on a road. At any given moment, the car has a single velocity vector that describes its speed and direction. For example, if it's moving at 60 kilometers per hour north, that's its velocity vector. Now, we don't say the car is moving at two different velocities, like 60 kilometers north and 80 kilometers south, at the same time. That would make no sense. The car is always in one state with one velocity vector at any given moment. Similarly, when we talk about a spinning coin, it's not simultaneously heads and tails when we measure it. At any given moment, it is a single state, heads or tails. Quantum superposition works the same way. While a qubit can exist in multiple states, when we measure it, the superposition collapses, and the qubit chooses a definite state. Just like the car has a definite velocity vector, or the coin lands on either heads or tails after it finishes spinning. Now that we've explored the idea of states and superpositions, let's talk about how we represent these symbols in quantum mechanics. We use something called bracket notation, or more specifically, ket notation. The vertical line and angle bracket are a shorthand way of describing the state mathematically. Let's talk about how we measure the probability of a quantum state. When a qubit is in its superposition, it doesn't mean it's partially heads and partially tails. It means it has a certain possibility of it being measured as heads or tails when it's observed. In mathematical terms, we calculate these probabilities using the coefficients in the superposition state. To find the probability of every state, we square the magnitude of the coefficients. For example, the chances of heads coming out of heads is 1, or 100%, or the chances of tails coming out of tails is 1, or 100%. It also works the other way, so the chances of tails coming out of heads is 0, or 0%, and the chances of heads coming out of tails is 0, or 0%. Let's work through a real example. Imagine a qubit in the state 0.819 for heads and 0.574 for tails. To find the probability of measuring heads, we multiply everything by heads to find the chances of heads. Because it is impossible for heads to be tails, that cancels out. So we are left with 0.819 times 1, which is 0.819. We square our final result to get the chance that it would be heads at 0.671 or 67.1%. That means that there's a 67.1% chance of observing heads. To find the probability of tails, we subtract this from 100% and we get 32.9%. So in this superposition, we have a 67.1% chance of observing heads and a 32.9% chance of observing tails. These probabilities represent the likelihood of each state being measured when we observe the qubit, not a mix of states. So what does this all mean? Why is quantum computing so important? A regular computer, like the one you're probably using, performs calculations by processing one state at a time. Each bit is either 0 or 1. It's a bit like flipping a coin and checking whether it's heads or tails, one flip at a time. But a quantum computer works differently. Instead of using regular bits, it uses these quantum bits and can perform calculations simultaneously. This ability to process multiple possibilities at once is what gives quantum computers the potential for solving certain problems far faster than classical computers. Problems that would take millions of years on a traditional computer could be solved in a fraction of the time with a quantum system. Imagine you have a normal bit, which can be the states 0 or 1. Now if you have 3 bits, you can represent 3 distinct states. Simple enough, right? But with qubits, it's a whole different story. If you have 3 qubits, they don't just represent 3 states. They represent 8 possible states, or 2 to the power of 3 possible states. This is an exponential relationship. The more qubits you add, the more the number of states grows exponentially. At 300 qubits, you can represent over 10 to the power of 81 possible states, which is more than the particles in the universe. This exponential growth is one of the reasons quantum computers are so powerful. Even with a few hundred qubits, you can represent an almost unimaginable number of possible states, making it possible to solve incredibly complex problems far beyond the reach of classical computers. Now, there's a catch. While quantum computers can represent all of these possible states at once, when you actually make a measurement, you can only get one result. This makes quantum computers less useful for everyday tasks. like video streaming, sending emails, or browsing the web. For those applications, regular computers are best. To truly harness the power of quantum computing, we need a smart way to extract the right answer from all the possible states. This is the challenging part. It's not enough to just have all these states. You need to figure out how to collapse them into a single, meaningful result that solves the problem that you want to address. That said, quantum computers do shine in some cases. One of the most critical uses for quantum computing is cryptography and breaking the encryption that protect all of the data we use online. This includes things like credit card information, social security numbers, addresses, essentially everything we send over the web. Here's how modern encryption works. Let's say there's two parties, party 1 and party 2. Each party has a unique 32-digit prime number. These prime numbers are multiplied together to create a product, which is sent through the web. This product is what keeps our data secure. The key to this encryption is that the only way to access the original data is by finding these two large prime numbers. Party 1 and Party 2 each hold one of these prime numbers, but no one else knows what they are. To break the encryption, a party has to have access to one of these prime numbers. This is an incredibly difficult task using a classical computer, because finding these two prime numbers for such a large number can take years or even centuries. However, quantum computing can solve this problem much faster. They can leverage their ability to process many possibilities at once to break these large prime factorizations in a fraction of the time, making current encryption methods vulnerable to a quantum-powered world. So let's break this down and look how quantum computers can crack modern encryption. If we want to find the prime factors p and q of a number n, this is how it works. First, make a guess. Start with the number g, a random guess. Second, find the exponent r. You need to figure out how many times you have to multiply g by itself to reach a number that's just one more than the multiple of n. Third, use the exponent. With the exponent r you found, you can calculate the two new numbers. These numbers are likely to share factors with n, bringing you closer to finding the prime factors. Finally, apply Euclid's algorithm. Use this classic algorithm to find the shared factors between the numbers you calculated and n. This should give you the prime factors p and q. Now, you don't need a quantum computer to run these steps. A classical computer can do the job. But the process of finding the correct exponent r takes a long time, especially when we're dealing with large numbers. The key advantage of quantum computing is speeding up the second step, finding the right exponent r. Quantum computers can do this much faster than classical computers by using the power of superposition and parallel processing, dramatically reducing the time that it would take to crack the encryption. Quantum computers perform these calculations by splitting apart into two sets of qubits. The first set, we prepare a superposition of qubits capable of representing up to 10 to the power of 1,234. To achieve this, we would need around 4,100 perfect qubits. The second set is a bit simpler. We prepare around 2,050 qubits, which are used to process and keep track of the information while the quantum calculations are being made. Both sets of qubits would be left in a similar state, working in parallel. The quantum computer can use its ability to perform multiple calculations at once, eventually collapsing the states to give the prime factors of the large product. This is what makes quantum computers so powerful. However, there's a challenge. Creating perfect qubits is really difficult. At the moment, we don't have fully reliable and stable qubits. We only have imperfect qubits. These imperfections in qubits are a major hurdle in the current state of quantum computing. To deal with the imperfections, we need to use more imperfect qubits than otherwise necessary with perfect qubits. In 2012, experts estimated that it would take around 1 billion physical qubits to break RSA encryption. That seemed like a monumental task, and at the time, it felt like quantum computing was still a long way from being possible. However, just 5 years later, in 2017, thanks to massive advancements in quantum technology, that number dropped to 230 million qubits. Fast forward to 2019, and we're looking at just 20 million qubits. An incredible leap forward for just a few years. Companies like IBM have been leading the charge in quantum computing research, and they're optimistic that in the next few years we could see quantum computers powerful enough to break current encryption methods. The question now is, when will this breakthrough occur? As we continue to develop more perfect qubits, the number of qubits required to break encryption keeps dropping, and the timeline for when these curves will collide becomes a lot more real. The government has known about this threat for a long time, with them recently starting to mandate a switch to quantum-resistant encryption. Imagine we're working in a 2D plane. We start with two vectors, r1 and r2. By combining these vectors in different integer multiples, like 3 times r1 and 1 times r2, we create a grid of points called a lattice. Now let's say you have a point C. Your task is to figure out which combinations of r1 and r2 will bring you closest to point C. For example, you can move in the direction of r2 twice and r1 negatively twice. And boom, you're at the closest point in the lattice. Easy, right? But here's a trick. The vectors r1 and r2 are just one pair that could make the lattice. You could also use b1 and b2. And even though the lattice looks the same, the math to find the closest point becomes a lot harder. The reason it's harder is because the new vectors don't move you directly towards the point you want. They bounce you around in ways that makes it harder to solve. So instead of a straightforward calculation, it becomes much more complex. Now imagine we do this in 3 dimensions. The problem gets significantly harder because now you have to consider multiple points and directions at once. Even more so if we expand to 1,000 dimensions, with 1,000 dimensions taking one step in the wrong direction could lead you to a completely different part of the lattice, making it nearly impossible for a quantum computer to solve. Here's how we can use this for encryption. Each person has a private set of vectors that creates their lattice, but they don't share these vectors. Instead, they share a publicly available lattice created from a complex set of vectors. To send a secret message, we pick a point on this lattice, add some random noise to it, and send it. The recipient uses the private vectors to decode the message by finding the closest lattice point to the one that was sent. Even though quantum computers can do some calculations really quickly, the complexity of this lattice-based encryption methods will keep our data secure for a very long time. Now there's another exciting way that quantum computing could shape our future, and that's with neural networks. In classical machine learning, we use algorithms that mimic how the brain works to learn from data and make predictions. But as data grows larger and more complex, these classical methods can become slow or inefficient. This is where quantum computing comes in. Quantum computers can process huge amounts of data at once due to their ability to exist in multiple states at the same time, thanks to superpositions. This allows them to handle and analyze large data sets much faster than classical computers. In the case of neural networks, quantum computers could significantly speed up training times. To understand neural networks, let's start by taking a look at the perceptron. It's a single layer of decision-making in the network. Imagine we have an image, and we're trying to decide whether it's a cat or not. The perceptron looks at the features of the image, like pixel values, which are just numbers representing the brightness of each pixel, and it assigns a weight to them. The weight tells the perceptron how important the pixel is for the decision. For example, a pixel in the center of an image might be more important than a pixel in the corner. There's also a bias. This is like a shifting factor that adjusts the output. It helps the perceptron make decisions, even if all the inputs are zero. Here's how it works in the code. The perceptron multiplies each input by its corresponding weight. It adds them all together plus the bias. This result is then passed through something we call an activation function. This is like a decision maker that says, yes, it's a cat, or no, it's not a cat. In a very simple case, the perceptron might look at a few features of an image, and if the weighted sum of those features is above a certain threshold, it classifies it as a cat. If it's below, it says no, it's not a cat. Now let's take this a step further. What if we want to make the computer more powerful and help it recognize more complicated patterns? This is where the multi-layer perceptron neural network comes in play. Instead of just one layer of decision making, like the single perceptron, a multi-layer perceptron neural network has multiple layers. The first layer still receives the input data, just like in the perceptron, but instead of outputting a final decision, it passes its output through more layers of decision making. This process repeats through multiple layers until we reach the final decision. Here's the advantage. By using multiple layers, the neural network could look at the data in a much more sophisticated way. For example, in an image, one layer might learn to recognize edges, another layer might learn to recognize shapes, and another layer might learn to recognize faces of animals. To help us better understand the way we can use neural networks in the real world, I'm honored to introduce Michelle Pokrass, a distinguished leader in the field of artificial intelligence. Michelle has an impressive background, having built massively scalable platforms at leading tech companies such as Google, Stripe, Coinbase, and Clubhouse. Currently, she leads the API platform at OpenAI, where she has been instrumental in developing and scaling AI technologies.
Yeah, so I've been working on the API at OpenAI, and so the API is a product for developers. It's not for your everyday user. So it's people who build their own applications and they want to build AI into them. So a few examples of users is someone like Snap or Apple. They have an integration with ChatGPT as well, or even like Morgan Stanley. So they are not using ChatGPT directly, but they're kind of building it into their product. So we like to make the API really easy to use, so developer can get stood up quickly and it's easy to integrate. And the 80-20 here is like, you don't want to make the application already done because the developer doesn't do anything. You want them to like imbue their own product, kind of make it their own a little bit, right? Like the Apple, ChatGPT integration doesn't look exactly like ChatGPT, so they provide, their own 20% of the application.
That's so cool. So you basically help developers make products, and then it makes it more accessible to everyday users.
Exactly, yeah. That's why, OpenAI will probably never build products in every vertical, but you can imagine like, an AI product for doctors or an AI for insurance professionals, and all of that will be built on top of the API.
You also mentioned that you prioritize making your services, as you say, easier for developers to integrate individuals to use. From an outsider's perspective, it seems like having a switch to prioritize the usability of a platform marks a turning point in the software's evolution. Are we reaching a limit to the power of artificial intelligence with our current technology?
I don't think so. We actually just released a much more powerful model in the API. It's called O1. It's a model that can think before it responds. It makes it quite a bit smarter, and you can see on like graduate level benchmarks, like vastly outperforms our older models. So I actually think I don't really agree with the premise that technology is getting more advanced, but also, it's still worthwhile to invest in making it easier to use, making developers easier to get started. This way you just get way more people building on the platform.
So just kind of like spreading it around. So you're making it better, and you're also helping users to better get like familiar with it.
Yeah, it's like if you've heard of other developer companies like Stripe, they're a payments processing platform, but their whole thing is that it's extremely easy to use, just a few lines of code. And that's kind of our goal with the OpenAI API, is just a few lines of code and you can integrate AI into your app.
Do you guys see like quantum computing or other growing technologies with lots of research going behind them helping you guys in the future?
I mean, quantum computing will be like a totally different paradigm in AI. Like I imagine, you'll have different types of models once quantum computers exist. I think we're quite a ways out from that. But I have heard some folks working on more thermodynamic-based AI.
There's also a debate about whether prompt engineering is a skill that will remain important as AI improves, and eventually, like, will it become obsolete, do you think? What's your perspective, and do you think understanding how ChatGPT processes information is really important?
I think over time, it will still be important to clearly outline what you want. people often say that they don't believe that there will be software engineering in the future, and I disagree with that. I think it'll just look different. It's still really important to explain exactly what you want. Everyone's had that experience where they type in like a not very good prompt to ChatGPT and they don't get anything back. But I think kind of the amount of effort you need to spend in prompt engineering will probably go down. But yeah, it'll always be important to like clearly state what you need, because otherwise, no one will be able to figure it out.
So you have to state it. It's not gonna be able to read your mind, basically.
Yeah, totally.
What are the key differences between the simple models we build and train and the massive models like ChatGPT?
Yeah, there's a lot of difference. I would say the main difference is scale. So the models behind ChatGPT are like, I think we publicly said GPT-3, I think, is in the hundreds of millions of parameters, something like that. Whereas your model, you can probably tell me, but it was probably, under a few gigabytes.
Yeah, it was.
And so it's actually very hard to express kind of, all of human thought into a small number of parameters.
Mm-hmm.
And so there's actually a paper on scaling laws, which describes, how the training data and the size of the model you use kind of causes, like, there's a curve in what kind of performance you can get. So one reason is scale. Like, our models are much bigger. There's also scale in the different direction, which is like how much time you spend training them, how much compute you spend. And there's also data. So you're training, on thousands of examples, but we're training kind of on things the scale of the entire internet, or like all words ever produced by all of humanity. So I would say those three reasons are kind of why there's scale. And finally, there's like architectural differences. So you're probably not using a transformer architecture. Transformers, are a great innovation. There's other innovations that aren't public. And so architecture and scale, I would say, are the main two things.
Many students today are familiar with voice assistants like Siri and Alexa. How does ChatGPT differ in terms of natural language understanding and generation from these systems, especially when it comes to handling more complex queries and tasks that you ask it to do?
Yeah, so a lot of traditional voice assistants are kind of a bunch of things stitched together. So one is like speech recognition. So it might be a separate machine learning model just to detect speech. One out there from our company is Whisper, which just transcribes. And then you have something, in the middle to be the brains of the thing. And often for things like, Google Assistant, it's actually not a model, or like a more primitive model, or like maybe a decision tree. It's like, if there's timer in here, then like set a timer. And then they'll have the final part, which is like the text to speech. So they'll use a separate machine learning model or even stitch together words to get the text to speech. And so you have to like put that all together. Whereas our voice mode actually combines all of those things into one model. And so that means that this model like takes in audio and produces audio. So it's much more native. And the model can like reason about things in the audio that would be hard to transcribe. So like you can imagine the first system, you get the transcribed text, but you don't know, like, was the person whispering, or was it loud, or was it quiet? Whereas because it's all natively in one model, then we can kind of use, emotional cues and respond that way. So it's just like a much more natural way of speaking, and it's just like much easier to use.
What elements of artificial intelligence have the most potential to be developed further?
I mean, broad question. I think overall, all models will get better. Reasoning will get better. I think cost and latency will go down. We continue to make things more efficient. I think we'll see robotics get really good. We're starting to see really good AI-powered robotics companies. So I can imagine 5 years from now, a lot of people have a robot in their house that folds their laundry. I can imagine that a lot more of like the economy is powered by AI. So a lot of mundane tasks might be done by, AI, and people have time for more creative work, or, they can just get a lot more done because they have more powerful tools. I think multimodal will keep getting better.
So what do you think is the job outlook?
I think of this moment is kind of similar to kind of the calculator or the camera moment. Calculator used to be a job, and the actual physical calculator disrupts that job. But what we see instead is that people, are able to be much more productive because they have this tool. And similar for things like Excel, right? Like accountants now and people in finance would struggle to do their jobs without it. And so I think we'll see something similar. I think people will always be doing productive work, but their tools will just get dramatically better. And then in the arts, I mean, a lot of art used to be, photorealistic, right? And then the camera was invented, and photorealistic is kind of a lot less interesting. And then so then you see kind of more abstract and modern art movements. So I think we'll see AI art become kind of its own genre. So I wouldn't worry about the job prospects. I think for one, it's a really good time to be a computer native because you can just use this technology a lot better. But I think in general, it will make really good tools for everyone, for teachers, for doctors, for insurance. And as you create more opportunity, people do more and produce more. And this is why our economy grows over time. It's because we're becoming more productive.
I think that's it.
Cool.
Thank you so much.
Yeah, no problem.
Today, we have explored the exciting world of quantum computing and machine learning. We've seen how quantum computing holds the potential to revolutionize industries by solving problems that would be impossible for classical computers. While quantum computing isn't ready for widespread use, we've learned about the advancements being made and the challenges still ahead, especially with building more perfect qubits. We also explored about how machine learning, particularly with neural networks, is reshaping how computers learn and make decisions. From simple single perceptron neural networks to multiple layer perceptron neural networks that recognize images, patterns, and much more, we've seen how these systems are improving the way we interact with technology. As quantum computing continues to evolve, it can unlock even more potential for machine learning algorithms, leading to a smarter, faster, and more efficient use of AI. It is an exciting time to be a part of the field, and I believe the innovations we've discussed today will shape the future of computing, cryptography, and artificial intelligence.